got the floor on the ball, you've got the earth on the ball, nothing's going anywhere, and those two forces are equal, we're going to write down something that I like to call an F-net equation. Has anybody ever heard the term F-net before?
Absolutely not.
Absolutely not, says one. Anybody heard it before? The answer can be no, and that's fine. I'm just curious. Let me tell you what it means. New information for your day today. You go home, your parents say, hey, what'd you learn today? Now you can be like, I learned what F-net means. F-net means the total of all the forces acting. So if I add up the floor force and the earth force, what are they going to add up to, friends? They are. If I write this out, I've got the force of the floor and I've got the force of the earth. And I notice that the force of the earth is going in the negative direction, isn't it? You told me that they're the same size in opposite directions. That means that they should add up to 0. So far, so good?
Yes.
I think maybe we drew the free body diagram for part B, but we didn't get a chance to talk about it. Is that true? Or did we not even get that far? Oh, okay. Well, then I'm going to give you 30 seconds right now with your table mates. You just saw it again in case you forgot. Excuse me, to draw the free body diagram for part B. Give it a shot right now. If you haven't done it already, do it right now. Free body diagram for part B. That's the part where I'm pushing on the ball. Go, go, go. Have that conversation. Make it fast, friends. We don't have a lot of time. We're moving fast today. Question? Yeah.
The lines also go up or down, or can they go?
They can go other ways too, can't they? Yeah.
I just noticed that.
Right. Yeah. So the game here is that we're like I'm adding new things every time. Yeah. Yeah. New layers, new interesting things. All right. Brian, how many forces do you have?
How many? What do I have?
How many forces? How many arrows?
Not enough.
2. Can you tell me what one of them is?
Gravitational pull, or force of the earth on the ball.
There you go. I love it. The force of the earth on the ball. And that one goes which way? Down. Straight down towards the center of the earth, right? So the force of the earth on the ball. I'm going to put FG in parentheses again to remind myself that is that gravitational force. Okay? But every time I draw it, I need my arrows to come from my dot, and I need to say earth on ball. Every time. Every time. Any other forces acting on my ball right now? Got another one. Force of the ground on the ball. Which way does that one go? Up. Same as it was the last time, right? Yeah. I labeled it force of the floor. I'm going to do that again just for consistency. But if you labeled ground before, that's fine too. Force of the floor on the ball, force of the ground, force of the surface, whatever you want to call that. How do those two forces compare? They are equal. They are indeed the same length. Is that it? It is not. Annie, did you guys have another force back there? Anybody from your table is welcome to share.
We have like one going forward, force of the other.
Yeah, I think that makes sense because I was pushing on it, right?
Yes.
Remember we said a couple days ago that a force is an interaction between two objects, and my hand was interacting with that bowling ball, right? There was contact. I was interacting with that bowling ball, so I'm going to go ahead and add a force, the force of my hand on the ball. In this case, with these three forces, is the net force, the total force on that bowling ball, is it 0? It can't be, can it? Because I've got the floor and the earth that are pulling in opposite directions, but then I added this extra force in there. So I think it's fair to say that the net force in this case is not 0. Remember I said that this trimester we're gonna talk about it this way. We'll do the mathy part next try. But for now we're good for now. Okay? All right. So this ball was sitting, then the ball was pushed, and then part C, the ball was just rolling, right? I'm going to give you 30 seconds. Right now, I want you to talk. I want to hear people having conversation about the forces acting on the ball for C. Go, go, go. I need to know what forces are acting in case C. So I want to talk to new, fun faces that haven't said anything yet. So I need some people who haven't talked to me. Who hasn't talked to me? If you volunteer first, then you get to tell me maybe an easy one, perhaps. Ooh, pick me. Go, Luke, what you got?
The force of gravity on the ball.
It's the force of the what on the ball?
The earth.
The earth on the ball, but it is a gravitational force, indeed. And which way does it go? Down. Yeah, it does. Everybody got that one? Oh, I'll get it in just a second. Thank you. Fantastic. Dawson, what you got, my friend? Where does it go? Up. All right, let's do it. How do those two forces compare? The floor on the ball and the earth on the ball. Same. See some patterns here? All right. Anything else? Put your hand out. You're like hesitatingly putting. Yeah, go ahead, Ed.
The force of the movement.
The force of the movement of the ball. What do you mean?
So when you push it, it gets set it in motion. It's still in motion and it's still going in that direction.
That's true. I agree. Do you guys agree that the ball is still moving?
It's rolling.
Okay. Question though. A force has to be an interaction, doesn't it?
Yes.
It does. Between how many objects?
2.
2. And so I appreciate you saying that, right? But I need to know what the other object is. So the ball is 1. What's pulling or pushing on the ball? So do we like air? Let me ask that question. No, air is bad. Get rid of air. So we're not going to worry about air resistance. I'll make a note of that because when you are an engineer, you do need to worry about air. But for today, as physicists, we're going to say no air. Okay? So no air. I need an object that's pulling or pushing on the ball if I'm going to draw an arrow. What would friction be doing? Would friction be keeping the ball rolling? Drake, what are you saying? It would slow it down, wouldn't it? Now, do you guys remember we had this bowling ball out way at the beginning of the year, and we went out in the hallway. Do you remember this? Got stopwatches and we were doing all this stuff, and we graphed it. And when we graphed the motion, I don't know if you remember, this has been a long time ago, but it was so much fun that we did this together. It did like this, and we did a position versus time graph. And do you remember what that position versus time graph looked like? I see lots of like straight line things going on. Straight line means what about its motion? Constant what? Constant positive what? Velocity. I need like a thing there, right? Constant velocity. And so you're saying if there was friction, what would that be doing to it? Slowing it down. In this very small case, do you think that bowling ball was slowing down very much? Not very much. Like if we did this like the whole length of the city, then sure. But if I've got this really nicely polished bowling ball on this really nicely polished floor, the friction is going to be so minimal it doesn't really count. So we're going to say no air, and we're also going to say no friction. We'll get to friction soon, I promise. Yet today, what else is pulling or pushing on the ball as it's rolling? Anything else pulling or pushing on the ball as it's rolling? Is my hand pulling or pushing on the ball? No, because I'm not touching it, right? And as much as we like to believe that Star Wars is real, right? The Force is not a thing. Spoiler alert, sorry, it's just made up. I'm sorry, Cole, I didn't mean to ruin your day. Okay? So there's no, I don't have any ability to like move the ball with my hand from far away. Is there anything else pulling or pushing on this ball? There is not. If you wanted there to be, I don't blame you, because a lot of people do. Because why? What is the ball doing? It's rolling. It's moving. But here's the thing. Is it speeding up or slowing down? It's not. In this very bottom box here, we're going to write down that the acceleration of that bowling ball as it's rolling is equal to what? It is. It's 0. And if I add up these forces, friends, F net, if I add those forces together, what do they add up to? Oh. Friends, take a look at A and C. Ignore B for just a minute. How does A compare to C in terms of the free body diagrams? They're the same. Same. They are exactly the same. But they're not. Why not?
Because this ball's moving in C and at A is that.
It's true. It's weird. This one's at rest. This one's at moving. But in both cases, they are not what? They're not accelerating. That is the key. In both of these cases, there is no acceleration. Right? Good thing you were here today. Like, this is a big deal day. Now, quick question. Let's compare. In A and in C, there was no acceleration. How about in B? Did the ball accelerate? Because I'm pushing on it. Look at you. You got this. The acceleration is not 0. You guys got this. This is it. That is it right there. Let's do D because we got to complete this whole story. So in D, go ahead now and draw the free body diagram. Label it very carefully. And you can even fill in these if you want. Fill in that whole column and then we'll come back in just a second and compare. Sound good? You got this, you guys. So much empowerment in your physics right now. Holy cow. Yeah, all right, let's do it. Let's do it. All right, ball is being stopped. Tell me a force. Let's see. Who's going to do this? Cole, did you want to do one? Tell me one of them. Go for it. Indeed. Where does that one go? It does. Every time. Have you noticed this pattern? Yeah. I'm going to write it as FG because we're going to come back to that in a second. All right. Any other force? Any other forces acting? Go ahead. Indeed. Yeah. So there's a force going this way, right? With the foot. The force of the foot on the ball. All right. That's 2. Anything else? Yeah. Where does that one go? It does. Fantastic. How does the force of the floor on the ball compare to the force of the earth on the ball? Oh, shall we mark that? Let's do it. All right. Is the net force in case D 0? It is not. F net does not equal 0. And hey, quick question. Does the ball accelerate in part D? Does it change its velocity? Because it was going, and then it stopped. Going to stop means change in velocity, means acceleration does not equal 0. You guys are rock stars. We doing okay? Sweet. We're going to turn that page over. And I intended for this to be just like a nice little organizational tool for you. Okay? Organization helps me to get things straight in my brain, and I hope it does for you as well. We're going to just list forces. We're not going to do all of them today. We're going to do a couple, and then we'll do some problems. We'll just kind of keep going back and forth and back and forth. The first kind of force that we acknowledged when we started dropping that frog, a couple days ago, was what? Gravity. It was gravity. We're going to write that down as the first force. F sub G. Gravity. Remember, every force has to be an object pulling or pushing on the object in question. What object is pulling or pushing when we're talking about gravity? The Earth. Is it always going to be the Earth? What if I go to the moon? That'd be the moon, right? If I'm talking about going around the sun, it'd be the sun. But in our cases, for most of our situations, yes, it's going to be the earth. I'm going to say the earth, unless otherwise noted. What direction does the force of the earth always act on that object? Down, yes. I'm going to say towards the center of the earth. Okay? Towards the center of the earth. I added this little diagram thing here just to kind of remind you what it should look like on a free body diagram. So I'm going to go ahead and put my little object and a vector, an arrow pointing down. This is the force of the earth on that object, whatever that object is. And then a quick question for you. Is the force of gravity able to cause acceleration? Yeah, we've been talking about that acceleration for a while, haven't we? Give me an example of that acceleration. Dropping an object, yeah. Okay. One down. I'm going to flip back for just a second to the other side, like the other, you don't have to necessarily turn around, but, or not that one. Come back. There it is. There's another force that exists in all four of these examples. What is that force? The floor, the table, whatever it is that's pushing it up, right? It's a surface. The surface is pushing on the object. Do you have a surface that's pushing on you right now? Yeah. The chair, right? The chair is pushing up on you, okay? The cool thing about these surfaces is that they push back the amount that they need to. It's kind of a funny deal, okay? These forces have a very special name. I'm going to show you a little picture here and tell you a little bit about them, and then we'll write them down on your chart, okay? These forces are called normal forces. Normal does not mean regular, plain old, unexciting, the norm. That's not what it means. There is a mathematical term, normal, and that's what it's referring to. Has anybody ever heard the term normal in math before and maybe retained it? You've probably all heard it at some point. Does anybody remember what it means? It's okay if you don't, I'm just asking. Let me tell you. Now you can wow your math teacher. You ready? Here it goes. Normal means perpendicular. Normal means perpendicular, okay? And a normal force is the force of a surface pushing on an object pushing up on an object. So you remember from chemistry that all objects are made of molecules, and those molecules are connected by bonds, right? Okay, and from a physics perspective, we can look at those bonds as little springs. And so this is like the very surface of my table or my floor or my chair or my whatever, okay? And then I put an object on that surface. And when I do that, the surface ever so slightly is deformed. I could pretend like this is my little frog. So here's his eyes and there's his feet, okay? And my frog is pushing down on the surface. Now, if I put my frog on the surface, everybody take a look here. I'm going to put it right here on this table. Ready? 1, 2, 3, go. Can you see the surface bending? Guys! Now, let me ask you a question. If I took 7 frogs and I put it on the table, would you see it bending? No. What about 7,000 frogs? 7 million frogs? 7 trillion frogs? Maybe, right? Eventually that bending is going to do what to the table? It's going to break it, right? So sometimes people do this in, like, I'm thinking like 3rd grade science fair projects. So I pulled this picture out to just kind of give you an illustration of this, right? So this is like the, which paper towel is the strongest when wet, right? You know what I'm talking about? So you get all these different kind of paper towels, but put them on these glasses and then they put pennies on them. So if you imagine you take that paper towel and it's all wet and then it's just sitting there and it's all happy and good. You put that penny on and it gets deformed a little bit, and then you put another one and it gets deformed a little more. Are you with me there? Okay? And if you put too many pennies on it, what's going to happen to the normal force, that force of the paper towel pushing back? What's that? No, I want to know exactly what you said because I think it was exactly right.
I think it was right.
What'd you say, Cole?
the paper towel will have like enough force to
That-
push it back up.
Yeah, that's perfect. Thank you for sharing that. So eventually, that paper towel, that surface, can't push up enough. You with me there? But until then, the paper towel is pushing back up. That's the normal force. That's all it is. It's not magic. Okay? It's just the surface pushing back up. All right, we're going to write this down in our force inventory. Second one, F sub n, the normal force, F sub n.
Are we not worried about magnitude today?
We are not worrying about magnitude today. In fact, we're not going to worry about magnitude at all this trimester.
Good.
We come back, next trimester, we'll totally do it. For now, though, this is what we got. What is the object that's pulling or pushing when we're talking about a normal force? Some sort of surface. It can be a floor, it can be a table, it can be a chair, it doesn't matter, but it is some sort of surface. Could be anything. What is the key for the direction? What does normal mean? What did we just say? Perpendicular. Sometimes it's opposite of a certain thing or another, but not always. And that's why we have to retain the information that normal means perpendicular. So the direction will always be perpendicular to the surface. And we will do some examples where it's not quite what you would expect, but we're not going to do them today. Okay, so I just want you to know for now that it's perpendicular. So I'm going to draw a diagram. My diagram needs to include some sort of surface. So I'm just going to go ahead and make just a little horizontal surface there. And then I've got my object. And it's always going to be perpendicular. And we're going to say that it is the force of the surface on the object. That next column says, is it able to cause acceleration? That's the gut feeling, right? We're gonna put it in parentheses with a little question mark right now. Spoiler alert, we'll change it later, okay? But for right now, you can go ahead and say no, because it doesn't feel like it's going to, but you just be patient, okay? All right, we're gonna go back to our examples again here. I think it's right here. There's one more force that we had in two of the four cases. What do you see? The hand, the foot, those kind of outside objects, right? Okay, that's going to be another one of our type of forces in our, oops, not that one. I want to go back here to force inventory. We're going to go right over here to the next one, and we're going to call this applied force, F sub A. Okay. This one's a little bit of a catch-all for things that don't fit into another category. So it's not a surface. It's not a gravitational force. It's kind of something else that may or may not be pushing, or that may be pushing, okay? So it's going to be some sort of object. Come on. Okay, so it could be a person. It could be like an animal. It could be some sort of outside something, okay? But again, it's something that isn't one of these other types of forces that we'll get to. The direction varies. It might be horizontal, it might be vertical, or it might have a little bit of both. Living on the edge, right? Woo, you never know. So I'm just going to draw a diagram just so we can get the label right. I'm just going to put it up like this. I'm going to say the force of, I don't know, I'll say a person in this case, on the object. And what do you think? This is kind of all the up that there is on this. Yeah. Do you think that it's able to cause an acceleration? Yeah, because we saw that it did, right? Yes, of course. Okay. How are we doing, friends? We doing okay? Fantastic. Okay, so we're going to go through just a little bit more stuff today, and then you'll spend some more time with this tomorrow. Okay, I usually just give these to you in notes. Hold on, don't put stuff away yet. Don't put stuff away because we had more to do. But instead of doing just regular notes, I put this out on a sheet because I thought it might be helpful. So I'm going to kind of pass these back if I'm not counting them out, so just grab one and pass them back. Grab one and pass them back. And we're gonna take a look at this here real quick. Hopefully I got enough to share. This is just like a notes opportunity for you to keep things organized a little bit. Take a look at the front. Okay? The front has 4 examples on it. There are 4 examples that we have already done. The first one says a frog falling. That was example 1 that you put in your notes. Number 2 is the frog sitting. We also put that one in our notes. This was a few days ago. Example 3 says a bowling ball rolling. We did that one today, didn't we? Yeah, rolling, rolling, rolling. And then number 4 was the bowling ball being pushed or stopped. The front of this sheet, you have absolute capability to fill out by yourself this evening, tomorrow, whenever you see fit prior to taking your your test. I would do it sooner rather than later, okay? I want you to turn to the back. We're going to do number 5 right now. So example number 5 involves one of my favorite Muppets, Rolf, who is the piano player. And the situation is that Rolf is pushing his piano across the room. It says that it's moving at a constant velocity. That's the information that I'm giving you. I would like you to draw a free body diagram of the piano. So the dot is the piano. Draw all of the forces that are acting on the piano. Go ahead and do that. I'll give you just a minute to do it, and then we're going to regroup and talk, okay? Go, go, go. You can talk to each other. You can have this conversation. That's amazing and awesome. Single time, I want you to have that. All right, let's do it, friends. So what have you got? What's one of the forces that you have? Go, Dawson.
I put F4 on ball.
Which way did that one go? Up.
Oh, my bad.
That's okay. I'll say piano. And hey, now we have a little more vocabulary with which to use. So what kind of a force is the floor on the piano in this way? Is it a gravitational or normal applied? It's a normal force. So we can write F sub n right next to it. That's really lovely. Awesome. All right, more forces. Tell me more. Go. Force of the earth on the piano. Which way does that one go? It goes down, straight down towards the center of the earth, right? That's a gravitational force. And my next question is going to be, how do these 2 forces compare? They are the same. So we're going to go ahead and mark that they're the same. It's helpful to know that. Are there other forces acting on the piano? Yeah, Haley, what you got?
Ralph pushing the piano.
Yeah, he's pushing on it, isn't he? Rolf. It's kind of a weird name. But I guess every name's a little funny, so you know. All right. Rolf on the piano. What kind of a force is that one? That is an applied force. Absolutely. What else you got? Or is that it?
This is off topic, but Ralph, Sesame Street.
Muppets. So Jim Henson made both Sesame Street and the Muppets. So the Sesame Street is kind of a subset. We can talk about that later. We have time to do that today. All right, so let's take a look down here. We're going to do this bottom one first. It says, is the object accelerating in the y direction? Is it's speeding up or slowing down in this direction? It is not. So we're going to say no. Can we write the net force equation just in the y direction? It's the same deal. We have F stuff and y stuff, right? What's going in the y direction? What do you got? The normal force and the gravitational force? Either of them negative? One of them, which one? Gravity? And they add up to? Indeed. All right. How about in the x direction? Is the object accelerating?
No.
I hear some dissension.
No.
Kaylee, what you thinking back there?
Well, it's moving at a constant velocity.
It says right there, it says it's moving at a constant velocity. If it's moving at a constant velocity, what does that tell us?
It's no acceleration.
It means there's no acceleration. And now I'm going to ask a really quick question here. Does our picture allow for no acceleration? Got one force pulling here.
That's great.
If I have just one force, is it going to cause it to accelerate? Probably. That means I've got to have something else. If I'm going to push my chair, let's pretend my chair is a piano, and I'm going to push it at a constant speed, what else has to be in existence in order for me to push it at a constant speed? I heard somebody say it. Jordan, was it
Chair's
you?
pushing back.
Friction. It's got to be there. We've got to have something pushing back. It's not air resistance. It's friction. We'll talk about it tomorrow, but I just want to make sure you see this. The force of the floor on the piano in the parallel direction, FF, if I add those together, and hey, how does this force compare to this one? How do you know that they're equal, Cole? Help him out. What's constant? The velocity is constant, which means there's no acceleration, which means those have to add up to 0. FA plus negative FF has to add up to 0. All right. Listen very, very carefully, my friends. Okay? We're going to be done with this. We're going to hand back tests, quizzes. Everything that you have taken, unless it was this morning, has been graded, has been put into PowerSchool. It's into Canvas, into Canvas. It's all there. If you have a 7-star and you want to make corrections, come in and do that so that you can bump that up to a 9. If you would like to do other things, let me know. There is not a retake on the Unit 2 test because we just don't have time, but there will be the final, which is like, it's just more opportunity, right? So make sure that you take into account all of those things